Hi, my name is Javier Rojas Ledesma. Thank you for joining me in this talk about the compact representation of a graph with efficient basic graph pattern query evaluation. We'll start by seeing what basic graph patterns are together with the motivation for our work. Then I'll present you an overview of the ring, our compact representation for graphs, together with some experimental results. And finally, we will be talking about some applications and limitations of our approach, together with some direction for future work. Graph databases have gained a lot of attention in recent years, and in this context, basic graph pattern queries are a powerful tool for understanding, extracting, and discovering information. This is why several commercial systems have tweaked their data structures and query languages to support them. We focus on a direct edge label representation of graphs, in which each edge has associated a label and is represented as a triple of subject, predicate, and object, the predicate being the label. The graph under this representation of edges is basically the list of these triples representing the edges of the graph. Under this representation, a basic graph pattern, or BGP for short, is also a directed edge label graph, in which now you can have variables both at the labels and at the nodes of the graph. For instance, if you have a graph representing the publications of this year's papers, that you can query for the co-workers that co-author a paper here at Sigmund using this basic graph pattern. Evaluating a basic graph pattern query is basically finding assignments for the variables of that are present in the BGP, so that when you replace these variables by their assignments, you end up with subgraphs of the graph that you have represented in your database. A BGP query can be expressed also as an SQL query. This is, for instance, the SQL syntax that is equivalent to the BGP of the previous slide. However, traditional join algorithms based on query plans in database management systems are known to be very inefficient for some of these BGPs. So that's why in the recent years, there's been a boom of new algorithms with stronger optimality warranties, in which the running time is bounded by the size of the worst possible output. These algorithms, known as worst-case optimal join algorithms, that are intuitively better for evaluating BGP queries, because BGP imposes a large number of restrictions on the outputs that are possible. And in fact, there has been several practical implementations of these algorithms showing that they behave good for certain type of BGP queries. However, most of these worst-case optimal algorithms rely on indices on databases that are heavily indexed, indices like P+3, for instance, that work only for a fixed order of the attributes. And in order to evaluate every possible BGP efficiently, they need that you index all your data in every possible order of the attributes that can appear in the BGP, meaning that you have high level of redundancy in your graph or in your database, and thus high space requirement. So our goal is to understand whether we really need this much space to support efficiently BGP queries. And I just want to point out that using less space is not only about the space itself, but also about the time, because if you have a light representation of a graph that fits, for instance, in the RAM, then algorithms evaluating queries could benefit from it by simply having all the data they need in the RAM instead of having to resort to disk to read part of the graph during the evaluation. And this means also that if your representation is small, then they could coexist with existing, for say, commercial databases with a small overhead, and improving considerably the execution of these BGP queries. There are previous work on BGP queries. For instance, there are several implementations of worst-case optimal algorithms for BGP queries. However, they rely on these indices and having this much redundant space that I just mentioned. And there is an implementation that it's compact and doesn't require any extra indices on top of the data, but it would be slow for medium to large size BGPs. So in this work, we present a compact representation of the graph based on text indexing techniques which can evaluate BGP queries in worst case optimal time, which we implemented a prototyping practice with very positive results. So in the remaining of this talk, I will give you a brief overview of the techniques that we use of our data structure together with some experimental results. I will start by giving you a brief insight on how we went from graph patterns to text indexes. We know that BGP queries can be evaluated in worst case optimal time using an algorithm known as leapfrog join, which in order for a graph representation to support this algorithm, you only need to provide an implementation for an operation known as leap. And we notice that if you represent your graph as a specially crafted text, then this leap operation is similar to pattern matching in strings. In this leap operation, you are given a set of equality constraints. Say, for instance, the predicate is 4 and the object is 3, and a greater than constraint of the form x is at least v for some x, which is a variable name referring to the subject, the object, or the predicate, and v is a value of the universe. For instance, the subject is at least 4. And this operation must return the smallest value c, such that when you add x is equals to c to the equality constraints, for instance, when you add s, let's say this c is 5, when you add s equals to 5 to the set of constraints that you already had, then there is at least some triple in the graph that matches the new set of constraints. Now, to later understand why this leap operation is somehow related to string pattern matching, and in fact to understand our graph representation, we need to know the concept of the Burrows-Wheeler transform of a text, or the BWT of a text for short, which is basically a permutation of the text obtained by generating this matrix with all the rotation of the original text sorted lexicographically and choosing the last column of the text. How can the BWT be useful in our context? Well, for first, it is reversible. You can obtain the original text from this permutation by using a function known as the LF mapping. Also, when you're searching for a pattern, the characters that precede the occurrences of this pattern in the text are all located in a contiguous region of the BWT, and you can exploit this property to find occurrences of patterns fast. Lastly, the BWT is usually easier to compress than the original text. So with this in mind, the key ideas of our representation and query evaluation is to regard triples as text and the graph as the concatenation of these triples, create a slightly modified version of the Burrows-Wheeler transform of text, so that as for pattern matching in strings, the output of any leap operation can be found in a contiguous region of this BWT. And then we index this BWT using wavelet trees to find this contiguous region fast, and finally store the wavelet trees using compact or compressed representation. Let us dive a bit deeper into each of these ideas, starting from how we go from a graph to a text. The first important part is to shift the triples so that the subjects are all smaller than the predicates and the predicates are all smaller than the objects. This can be achieved by summing n to all the predicates and 2n to all objects for n large enough. We then concatenate all the shifted triples to obtain the text T. And the importance of the shift is that if you now look at the BWT of the text, you notice that it is almost perfectly split into 3 sections, with all the objects first, then all the subjects, and then all the predicates. And that except for this last object at the end of the BWT. As I already mentioned, we don't need to store the text and the BWT at the same time, because using the LF function and starting from any position of the text, we can rebuild the entire text. However, if we want to retrieve one particular triple, this could be inefficient, since we could, if we use the LF mapping without any modification, we would need to rebuild the entire text, for instance, to get the object of this triple here. We solve this problem by slightly modifying the BWT. We take the last object and insert it at the end of the section of objects of the original BWT and drop the end of string character. So now we end up with slightly modified version in which you have at the beginning all the objects, then all the subjects, and then all the predicates of the triples of the graph. Moreover, we can show that if now you start applying the LF mapping function from, let's say, the ith predicate, instead of rebuilding the entire text, now you start to cycle through the different components of the triple. This cyclic behavior is not only useful to solve the problem of retrieving the ith triple, but is also key to our implementation of the leap operation. We can show that for any leap operation, there's always a contiguous branch in this modified PWT from which you can retrieve all the triples that match the set of equality constraints. When the set of equality constraints is empty, this branch can simply be the entire section of objects. If now the set of equality constraints, for instance, has exactly one element, let's say restricting the predicates to be some given value VP, then the subjects of all the triples with this value in the predicate must be necessarily, because of the way in which the PWT is constructed, must be in a contiguous region inside the zone of subjects in the PWT. The same goes for the other types of equality constraints. When you have two equality constraints, then you can also show that there's a contiguous region of the PWT where you find either all the objects, all the subjects, or all the predicates of the triples exactly that match the pair of equality constraints. So our leap algorithm first needs to find this contiguous region in the PWT of the triples matching the equality constraints, and then we show that within this region you can perform a binary search looking for the first or the smallest value which matches the greater than constraint of the leap operation. So basically, in order to perform leap operations fast, we just need to find this contiguous branch within the PWT fast. For this, we index the cyclic PWT using wavelet trees. Also a technique inspired from text indexing data structures, in this particular case, the FM index. And we showed that our representation requires only 3 n-log u bits of space plus some lower order term. Note that this is quite close to what you need just to represent the data of your graph. Then we show how you can support leap and retrieve operations on top of this graph representation so that they run in big O of log u time. And this running time is enough to implement the leapfrog rejoin algorithm on top of our graph representation so that you can evaluate basic graph pattern queries in worst case optimal time. So summing up, the ring, which is the name that we gave to our graph representation, is essentially a wavelet tree indexing the cyclic PWT of the text representation of the graph so that you can support fast leap and retrieve operations. And in turn, you can evaluate in worst case optimal time BGP queries by means of algorithms like the leapfrog rejoin. We implemented a version of our data structure using a compact representation of the wavelet tree and also a version using a compressed representation of the wavelet tree. To test this prototype implementation of the ring, we use a benchmark on Wikidata. We choose Wikidata because of its scale, diversity, and also because of the data model. We compare our implementation to state-of-the-art solutions using these queries. And here we show the queries for which the ring behave significantly better, similar, or significantly worse than the other alternatives. For these queries where the ring behaves significantly worse than the alternatives, the algorithms or the schemes beating the ring were empty-headed and QDACs, which are also two in-memory solutions, in this table, we show the comparison between our implementation of the ring with other graph databases in terms of the average running time of all the queries of the benchmark and the space in terms of bytes per tuple. Note that a raw representation of Wikidata uses 12 bytes per tuple and that the ring uses only 12.7 bytes for each tuple, which means that it only needs a 6% of extra space on top of the actual data, while still being faster than the other alternatives. We could confirm that the ring is between 4 to 11 times, uses between 4 and 11 times less space, while at the same time being between 2 and 30 times faster, depending on the point of comparison. Note, for instance, that while we are not the solution that uses the least space, in this case, QDAC uses even less space than the ring, QDACs are quite unstable, especially on queries like large paths, because of the exponential constant in the running time of the query evaluation. Also note that the closest solution, other solution in terms of running time, which is this implementation of leapfrog join using Jena, uses at least one order of magnitude higher space. Another relevant implementation, which is actually one of the solutions that in these queries where we are significantly worse than the competition, in several of those queries, the best alternative is empty-headed, which uses up to 2 orders of magnitude higher memory than the ring. So the main conclusion that we take out of this table is that the ring can compete with the alternatives while using a lot of while using significantly less space. As I said, we also implemented a compressed version of our graph representation, and this time this compressed version uses even less space than QDACs, while being only beaten in terms of the average running time by the leapfrog join implementation on top of Jena. So even this compressed representation is quite competitive with the other alternatives. So summing up, as we have seen, the ring is a compact representation of a graph based on text indexing techniques, which supports efficient evaluation of basic graph pattern queries by means of worst-case optimal join algorithms such as leapfrog join. Our experiments show that the ring behaves stable across all the queries, and it can compete with the other alternatives while using between 1 and 2 orders of magnitude less space. Not only can it compete with other worst-case optimal algorithms, but it beats in all the queries of the benchmark, all the commercial graph database systems. And this is precisely where we envision the main application of our graph representation, to use it as an addition to commercial graph databases so that they can solve BGP queries faster with a small overhead. And now let us briefly talk about some of the limitations of this graph representation, together with some directions for future research. For starters, this is an in-memory data structure that relies heavily on random access. Thus, it will be very hard to migrate efficiently to a disk storage. Also, our current implementation is read-only, is a static data structure. It can be made dynamic using standard dynamization techniques for compact data structures, but we need yet to measure the query time and how this impacts the query time. Also, our current implementation works only for ternary relations or for directed edge level graphs, but we believe it should be extensible to higher additive relations, and this is something that we plan to work in the future.